A heap is a special kind of binary tree that satisfies two rules. Complete tree property: every level of the tree is completely filled, except possibly the last level, which is filled from left to right. This makes the data structure easy to store in a simple array. Heap order property: for a max heap, every node's key is greater than or equal to the keys of its children. For a min heap, every node's key is less than or equal to the keys of its children. Because of these rules, the largest element in a max heap or the smallest in a min heap is always at the root index 0 in an array. Think of a max heap like a tournament bracket, where the winner, the biggest number, moves up to the top after each match. Both types of heaps are implicitly ordered. They do not guarantee any order among siblings, only the parent-child relationship. This is why searching for an arbitrary element still requires big O of n time, but extracting the extreme element is big O of log n. Storing a heap in an array eliminates the need for explicit pointers. If the root is at index 0, the relationships are: parent of I equals floor of I minus 1 divided by 2, for I greater than 0. Left child of I equals 2i plus 1. Right child of I equals 2i plus 2. These formulas work because the tree is complete. The nodes appear level by level in the array. For a one-based array sometimes used in textbooks, the formulas become parent of I equals floor of I divided by 2, left of I equals 2i, right of I equals 2i plus 1. Example: in the array 50, 30, 40, 10, 20, the element at index 2 with value 40 has left child at index 5 with value 20 and right child at index 6, which does not exist, so 40 is a leaf. The parent of index 3 with value 10 is floor of 3 minus 1 divided by 2 equals 1, which corresponds to value 30. The build heap or heapify algorithm turns an unordered array of n elements into a valid heap in linear time. This algorithm bottom-up. For I equals floor of n minus 2 divided by 2 down to 0, sift down I, restore heap property in the subtree rooted at I. I equals floor of n minus 2 divided by 2 is the last non-leaf node. Sift down moves the element at I down the tree until the heap property holds. Y(O) of n's. Consider the height h of a node measured from the bottom. Leaves have height 0. At height h there are at most ceiling of n over 2 to the power of h plus 1 nodes, and each sift down on such a node costs O of h swaps. The total work: the sum from h equals 0 to floor of log base 2 of n of ceiling of n over 2 to the h plus 1 times O of h is less than or equal to the sum from h equals 0 to infinity of n over 2 to the h plus 1 times h, which equals n times the sum from h equals 0 to infinity of h over 2 to the h plus 1, which equals n times 2, equals O of n. The series sum from h equals 0 to infinity of h over 2 to the h converges to 2, giving a tight linear bound. Thus, building a heap from scratch is faster than inserting each element one by one, which would be O of n log n. Explanation: insertion push adds a new key at the end of the array and then restores the heap property by moving the element up. This is called sift up or bubble up. The steps: 1. Append the new key x at index I equals size, the next free slot. 2. While I greater than 0 and heap parent of I less than x for max heap, or heap parent of I greater than x for min heap : swap heap I with heap parent of I. Set I equals parent I. 3. Stop when the parent already satisfies the order or I becomes the root. Example: max heap : current heap array 29, 12, 8, 7, 10, size equals 6. Insert 15. Append yields 29, 12, 8, 7, 10, 15, I equals 6. Parent 6 equals floor of 6 minus 1 divided by 2 equals 2, value 12. Since 15 greater than 12, swap 29, 15, 8, 7, 10, 12, I equals 2. Parent 2 equals 0, value 20. 15 less than or equal to 20, stop. Resulting heap satisfies the max heap property, and the new element rose only 2 levels. The work is big O of log n. The same logic with reversed inequality gives insertion in a min heap. Extraction pop removes the extreme element root and restores the heap property by moving the last element to the root, and then sift down, also called heapify down. The steps for a max heap: Step 1. Save max equals heap 0 the element to return. Step 2. Move the last element heap size -1 to heap 0 and decrease size. Step 3. Starting at index I equals 0, repeat. Let L equals left of I, R equals right of I. Choose largest equals I. If L is less than size and heap L is greater than heap largest, set largest equals. If R is less than size and heap R is greater than heap largest, set largest equals. If largest not equal to I, swap heap I and heap largest and set I equals largest, otherwise break. Step 4. Return saved max. Illustration. Heap before pop 2015 12 8 7 10, size equals 6. Save max equals 20. Move the last element 10 to root becomes 10, 15 12 8 7. Compare children of index 0. Left equals 15, right equals 12 becomes largest child 15 at index 1. Swap 10 and 15 becomes 15 10 12 8 7. Now at index 1, children are 8 and 7, larger child 8 at index 3. Since 10 is greater than 8, stop. Resulting heap is a valid max heap, and the operation cost is big O of log n. For a min heap, the comparison signs are reversed. The same procedure is called delete max for max heap and delete min for min heap. Heap sort uses the heap data structure to sort an array in place. Algorithm max heap version for ascending order. Step 1. Build heap the array, which is O of n. Step 2. For end equals n minus 1 down to 1. Swap heap 0, the current max, with heap end. Decrease the effective heap size to end. Sift down 0 on the reduced heap, which is O of log end. Step 3. After the loop, the array is sorted in ascending order. Complexity analysis. Building the heap is O of n's. The loop runs n-1 times. Each sift down costs O of log n in the worst case, giving O of n log n. Total time equals O of n log, and the algorithm is not stable because equal elements may be reordered during swaps. Space only a constant amount of extra storage. The heap is stored in the same array, so theta of 1 auxiliary space. Heap sort is attractive when you need a guaranteed O of n log n worst case bound, and you cannot afford extra memory, for example embedded systems. Heaps are the backbone of an efficient priority queue, a container that always gives access to the element with the highest or lowest priority. Push key inserts with big O of log n using sift up. Pop removes extreme with big O of log n using sift down. Teak reads the root with big O of 1. Because of these logarithmic bounds, heaps replace naive linear scans in many algorithms. Graph algorithms. Dijkstra's shortest path, the frontier of vertices with tentative distances, is kept in a min heap. Each extract min yields the next vertex with the smallest distance, and decrease key implemented as a delete insert updates distances, giving overall big O of open parenthesis v plus e close parenthesis log v time. Prim's minimum spanning tree. Similar to Dijkstra, a min heap stores edges crossing the cut. Extract min picks the cheapest edge that expands the tree, leading to big O of e log v for sparse graphs. Exam focus. Know how to argue the time complexity using heap operations, be able to write pseudocode for push, pop, and decrease key, and understand why a binary heap gives big O of log n, while a Fibonacci heap can improve the amortized bound for decrease key. Real-world analogy. A hospital emergency room where patients are treated according to severity priority. Adding a patient is like inserting into a priority queue. Calling the next patient is like extracting the max urgency. Write the index formulas for parent left and right child in a zero-based array. Identify the parent of element at index 7. Pitfall: forgetting to floor the division, using 1-based formulas on a 0-based array. Given the array 4, 10, 3, 5, 1, build a max heap using the bottom-up method. Show the array after each sift down call. Pitfall: starting the loop at the wrong index. Should start at floor of open parenthesis and -2 close parenthesis divided by 2. Implement push for a min heap. Explain why the loop terminates. Pitfall: using greater than instead of less than for the comparison, leading to a max heap behavior. In Dijkstra's algorithm, a vertex's distance is decreased from 15 to 9. Describe how this operation is performed on a binary heap and its cost. Pitfall: assuming decrease key is big O of 1. It requires a sift up, big O of log n. Why does the build heap algorithm run in big O of n time, not big O of n log n? Provide a short mathematical proof. Pitfall, forgetting that most nodes are near the leaves and require only few swaps. A common mistake is off by 1 errors, mixing 0-based and 1-based indexing when applying formulas. Violating the complete tree property, inserting a node without placing it at the next free leaf position. Sift up versus sift down confusion, using the wrong direction after insertion or deletion. Not updating the heap size after a pop, leading to out-of-bounds accesses. Assuming stability, heap sort does not preserve the original order of equal keys. Being aware of these pitfalls and practicing the index arithmetic will avoid most bugs on an exam.